So before we get started on our lecture, I want to talk about the test real quick that is occurring this Friday. What I want to talk about to you guys specifically is my memory isn't as great as it probably should be, so I can't remember whether or not we discussed the use of equation sheets in this class for the in-class portion of exams. So what I have done is I have created, if you go here to exam 1, there is an equation sheet that you will be provided for the exam. And it's downloading it because I didn't make it a PDF file, which I might do later. You won't need to bring this to class or anything. It's provided for you. And so what this is, where does the yellow bar thing here? So I have a practical op-amp model up here at the top, obviously labeled as practical op-amp model. Then I have open loop op-amp circuits. And so I just have a very generic and stylized version of, so for the non-inverting comparator, the input signal is applied at the non-inverting terminal. The reference is applied at the inverting terminal. There are power supply voltages, there's your output. And I tell you what the input-output relationship is. VCC plus for Vn greater than Vref, VCC minus for Vn less than Vref, and then obviously for the inverting comparator, it's a similar thing. Below that, I have positive feedback op-amp circuits, so specifically a non-inverting Schmitt trigger and an inverting Schmitt trigger. I'm not going to test you guys on the astable multivibrator at all, so that's why it didn't make it onto the equation sheet. But the equations that I have here are the equation that you use to calculate the upper trigger limit and the lower trigger limit and all that kind of stuff, and you need to algebraically manipulate it if that's necessary. And then for the second page, we have non-inverting amplifiers, inverting summing amplifiers, differencing amplifiers, differentiating amplifier, and integrating amplifier. With their characteristic of how they look. So by that, I mean, we can see that for a non-inverting amplifier, the input is applied at the non-inverting terminal. Ground is applied at that leg of that resistor. For the inverting amplifier, it's different. Effectively, I wanted to provide you guys with a table, I guess, to where you can pretty easily see, all right, so this circuit is configured in this way, so it must be one of these, and then move along. Because the expectation here is that, I don't remember exactly how many, I think I'm gonna have you analyze 5 circuits. And some of that analysis will be, okay, so identify what type of circuit it is, and then do, you know, X, Y, and Z, something like that. So that all in all, there's going to be somewhere in the ballpark of, I think, between 15 and 20 questions on your exam, and you only have the 75 minutes to do it. So I wanted to make sure effectively that you weren't struggling for 10 minutes. Oh, how do I do this for this particular type of amplifier? So I'm providing the equation sheet for you. With regards to studying and all that kind of stuff, I think the best thing that you could do is go back and look at some of your homework assignments and all that kind of jazz. Let me minimize this. So if we go to the homework section, I have uploaded a homework 5 and a homework 6. These are not due until after you take your exam, but the material covered on them. So homework 5 is negative feedback op-amp circuits. Homework 6 is cascaded op-amp circuits. While the homework is not due until after you take the test, that material is still fair game for the exam. Mr. Melson. I have a grader working on stuff right now. From what I have seen for the homework assignments, for the most part, everybody's doing things pretty correctly. For your exam, the take-home portion, excuse me, the in-class portion exam, it is going to be multiple choice, nothing wildly tricky or anything like that, meaning if you work the problem and you get an answer that's there, there's a 99.9% chance that you did it correctly. There's not really an opportunity for me to do that because I'm not asking you to calculate, absorb power versus supply power or anything like that. So for one particular problem that I'm working on, I give you I give you the output graph for a problem. And then from that graph, you need to be able to tell me, which voltage is VCC plus, which voltage is VCC minus, which voltage is VREF and all that kind of stuff. So I might have literally all of those voltages selectable for all of those different quantities. That's as tricky as I intend on being. If you have a reasonable estimate of being able to identify the circuit correctly based on what its output is, which should be fairly trivial for any of the not negative feedback amplifiers, you should be able to use your knowledge and the little table or equation sheet that I gave you to figure out which voltage is supposed to go where very easily. So that's as tricky as I intend on being. But I will get as many of those homework assignments graded and returned to you tomorrow as humanly possible. So how that's going to work is I have my grader working on things right now, and she is supposed to be uploading the grades. So she's supposed to be providing feedback on her tablet or whatever to the PDFs that you guys submitted, and then uploading all of your homework submissions into a personal folder on my Google Drive, and then I will share that folder with you individually so that all of your homework will get to return to you in the same place, and you can see all of the feedback so that you don't need to come to my office or anything dumb like that. It's all going to be online. Does that sound reasonable? All right. So before we move along to cascaded amplifier circuits, anybody have any questions about test format or anything? Sonny.
Is it going to be like the first part is like those have and
No, it's just going to be circuits to analyze in some way, shape, or form. We don't really have a lot of vocab kind of things and theoretical concepts here in this class that we didn't already cover in circuits 1. So it's, I would argue, not a waste of time per se, but we got better things to do than worry about that. At this point, you should know what current, voltage, power, energy, and all that kind of stuff is. Brandon.
We're ready to be grading one show one. Do you have like 5?
I can ask her. Yeah, I can absolutely ask her to grade anything that's been submitted. That requires me to get off my butt and get her the solution, which I have all the solutions and all that kind of stuff made, but they're just papers on my desk right now and not digital copies that she can have easy access to. So I'll get that taken care of tomorrow. I plan on getting here tomorrow at about 6 o'clock in the morning and just locking myself in the office and seeing nobody until I get everything caught up. That's my goal. We'll see how it goes, but if you guys are willing to leave me the hell alone, I'm willing to get stuff done. So.
I need to just take my homework.
There will be a tutoring session for those of you that may be unaware this evening from 4:30 to 5:30 p.m. in Neskin Hall. What is it? 105? I don't know the name of it, but it's the one just down the hall. All right. Any other questions regarding exam layout, etc.? Okay. So cascaded op-amp circuits. So let's say that we have the following amplifier circuit. I'm going to call this guy here amplifier A1. And assuming it's powered correctly, we have a 5 kilo ohm resistor acting as a feedback resistor for amplifier A1. I'm going to apply a voltage of 2 volts to the non-inverting input terminal. Let's put a 3 kilo ohm resistor here. Ground this leg. We're going to take the output of amplifier A1, feed it through a resistor, and then that will be some portion of the input for a second amplifier, A2. Where A2 also needs to be turned on or powered. And let's say that I have a 7 kilo ohm resistor here. This guy right here is a 20 kilo ohm resistor, and the output voltage of our chain of amplifiers is the voltage drop over that 20 kilo ohm resistor. This is an example of a cascaded op-amp circuit. We have the output of our first amplifier cascaded into the input of our second amplifier. Now, we're going to analyze this circuit as if we cannot easily identify what each of these stages is at first. And the reason we're going to do that is because I might give you something to where you can't easily identify one of the stages. So we need to know how to handle that. Then we're going to take a look at this circuit, splitting it down by stage and getting an overall general relationship. Okay. So we are going to apply nodal analysis at key nodes in our circuit. Okay. So I'm going to call this guy node A, this guy here node B, this guy here node C, and this guy here node D. So I've labeled the inverting input node for both of my amplifiers, and I've also labeled the output node for both of my amplifiers. And the reason I've done this is because this is the most likely places that you guys would probably try to apply the concept of nodal analysis to these circuits. Okay. Mesh analysis would be a very weird and odd thing to even attempt to do here, so I'm not even going to discuss that as an option. Okay. So if we applied Kirchhoff's current law at node A, we would be summing this current and this current together, right? Because we know that no current can branch off and flow into the inverting input terminal of our op amp. And so KCL at node A would yield the voltage at node A divided by 3 kilo ohms plus the voltage at node A minus the voltage at node B divided by 5 kilo ohms is equal to 0. We could then attempt to write the KCL equation at node B. And I say attempt to write for a very specific reason that you'll find out shortly. So, Sarah, what do you think my KCL equation at B should look like? All right, so VB minus VC over 10 kilo ohms. I agree with that part. What else? VB minus VA over 5 kilo ohms. Anything else? Right. So our ideal op amp rules tell us that no current can flow into or out of the input terminals of an op amp. Node B is the output terminal of an op amp, which means we could observe current flowing from node B back into our amplifier A1. The problem that we have is that our model has no way, shape, or form to account for this. So when we're using the ideal op amp model, we can't ever apply Kirchhoff's current law at the output nodes, because unless we're specifically trying to, unless we know what that output voltage is to begin with, right? We can't apply KCL at the output node to figure out what the output voltage is, because there's an unknown current relationship that we can't simply ignore there, okay? So KCL at B, so plus just some, let's call it I op amp 1 is equal to 0. Well, there's no way that we'll ever know what that is without knowing what V out is to begin with, okay? So we could use a practical op amp model, and then we could apply KCL at node B and we wouldn't have any issue whatsoever, right? So the key here is that if we're trying to use the ideal op amp model, we don't know what the internal resistances are because we're just saying they're 0. We're saying the gain is infinite. So it's still going to give us a problem because we don't have any finite values to relate things to. So KCL at our output node here is bad. We could write an equation for node C. Right? Sunny, what's my KCL equation at node C going to look like? All right, so VC minus VB over 10 kilo ohms. All right, and those are my only 2 contributions. If we tried to write a KCL equation at node D, we run into the exact same problem that we saw at node B. There's some current that could be flowing back into op amp 2 that we have no way to account for. So right now, we have two equations with 4 unknowns. So Ian, where are my 2 other unknowns coming from?
For equations or two?
Yes, my 2 other equations, sure.
We could use. I would assume it would be something along the lines of, we know current isn't going into like a inverting input terminal. So current through that 8 kilo ohm resistor should be current from VB to VC.
I think you're overthinking it.
Probably.
Okay.
If we
So
work
we've-
backwards and find the output time.
We've used our current constraint equation, no current can flow into or out of our terminals to write these KCL equations. At no point have we applied our voltage constraint equations that say the voltage at the non-inverting terminal is equal to the voltage at the inverting terminal, right? So if we apply those, we can see VA is 2 volts, VC is 0 volts, and those are our other 2 equations. We now have 4 equations, 4 unknowns, and we can easily solve. And we'll find that VA is obviously going to stay 2 volts. VB comes out to be 16/3 of a volt. C is 0 volts. And VD is negative 64/15 of a volt, okay? So that's the hard way. Give you guys a moment to digest all of this. All right. So we can write KCL equations for the inverting input terminals. And we can use our voltage constraint equation because we're dealing with ideal op amps to be able to get some relationship here where our output voltage in this case is nothing more than our nodal voltage VB. So we've solved the circuit, right? So we can make this significantly easier by dividing this circuit up into stages, right? So if I draw a dashed line right here, and I say that this node is the output voltage for V1 and also the input voltage for op amp 2, we can break this guy up into discrete stages that we can easily analyze, right? So we can actually do all the analysis that we need probably right over here on the right-hand side. Okay. So Brandon, if I call everything to the left stage 1 and everything to the right of my pink line stage 2, what kind of amplifier is stage number 1? Non-inverting. So it's a non-inverting amplifier because our input is applied at the non-inverting terminal and we have a negative feedback loop. Okay, so stage number 1 is a non-inverting amplifier. Cheston, what's my input-output relationship for a non-inverting amplifier? You need to look it up in your notes from Wednesday or no, Monday, by all means do it.
I'm not R over R.
Oh, that's not for a non-inverting amplifier. That was for an inverting amplifier. So what's the relationship for a non-inverting amplifier? What's the equation that we developed that says V out is equal to something multiplied by V in?
1 plus R.
Okay. So V out 1 will be equal to 1 plus RF over R1 times V in. So, Mr. Bodie, what's V in this case? 2 volts. Which one is RF? And which one is R1? All right, so we're going to have 2 times 1 plus 5/3. So that is the same as 3/3 plus 5/3. So 2 times 8/3 is 16/3 of a volt. Is that what we got for VB? Well, I'll be damned it is.
Why do you not specify that it's non-inverting negative feedback?
I don't, the negative feedback, I'm just using the labels that we have derived. So for the negative feedback amplifiers, we called this guy a non-inverting amplifier. I don't care whether you include negative feedback or not. But we don't have a negative feedback, or excuse me, we don't have a non-inverting positive feedback amplifier. We have a non-inverting Schmidt trigger. All right, so I'm just trying to use the names that we've utilized throughout here. So I call the circuit, like the left-hand side, which I've denoted as phase 1, a non-inverting amplifier, and we identify that it is a non-inverting amplifier because our input voltage is applied at the non-inverting input pin. Ground is applied at the other leg of the resistor that's connected to the inverting input pin, and we have negative feedback. All right. So, Mr. Parrott, what type of amplifier is stage 2? Absolutely right. Inverting amplifier. So V out, which is the output of that particular amplifier, what's our input output relationship for an inverting amplifier? Negative RF over R in or R1 or whatever I happen to call it. Times V in. So, Caleb, what's our input voltage for stage 2? 16/3 of a volt. And then we're going to have negative, what's RF? And what's R1? 10 kilo ohms. All right. So we're going to have 16 times 8 over, oh God, I should be able to do that. 64, 128 over 30, which is negative 64 over 15 volts. And it's exactly what we got doing it the long way. So if we can break our circuit up into easily identifiable and digestible bits, we can use our input-output relationships that we developed last class for common op-amp topologies and make the amount of analysis that we need to do for these cascaded circuits inconsequential. If there were a part of a stage here or something that we didn't recognize, we could go back and rely on the correct application of our ideal op-amp rules and all that kind of stuff just to figure out what's going on in that stage, and then use those results to build on stages that we understand. That's cascaded op-amps. That's it. Just chaining op-amps together and then making them do certain things. So for part of your design project thing and part of your take-home test, I'm going to have you design cascaded op-amp circuits to do specific operations. So for instance, one of the things that I'm going to ask you to do, I haven't decided if this will be on your exam or if this will be one of your options, will be how you would take a sine wave input and produce two outputs, one of which is a square wave and one of which is a triangular wave. So how do you think that you could make a square wave with a sine wave input? Well, comparator. Schmidt trigger will work, but that's going to give you a duty cycle that isn't the exact same. It might give you a duty cycle that isn't the exact same as the sine wave, meaning it's not going to be exactly on half of the time, or exactly high half of the time and exactly low half of the time, but a comparator will definitely work that way. How would you take the square wave and convert it to a triangular wave and integrate it? Exactly right. So if you can chain those two things together, you're good to go. That's how analog wave generators do it. And then you can vary the components to change the frequency. All right, so I don't know, we're 45 minutes early. What do you guys want to do?